Right now, something is flying through our solar system that does not belong here. It was not born here. It was not made by our sun. It did not come from any planet or moon or asteroid belt that we know. It came from somewhere out there. From another star. Maybe from a star that died before our sun was even born. It is a chunk of ice and dust about 2.5 kilometers wide, and it is moving at 210,000 kilometers per hour. That is fast enough to travel from Earth to the moon in less than 2 hours. And it is not slowing down. It is not staying. It flew in from the darkness between the stars, swung past our sun, and now it is heading back out into the void. We will never see it again. Its name is 3I/Atlas, the third interstellar object ever detected by human beings. And what we are finding inside it is rewriting what we thought we knew about how stars and planets form across the entire galaxy. But before we get to what makes this object so special, you need to understand something first. How do we even know it is not from here? Think of it this way. Every planet in our solar system, every moon, every asteroid, and every comet that was born here travels around the sun in closed loops. Some loops are nearly circular, like Earth's. Some are stretched into long ovals, like the orbits of comets that swing out past Pluto and come back. But no matter how stretched the oval is, it always closes. The object always comes back. It is trapped by the sun's gravity. Scientists measure the shape of an orbit using a number called eccentricity. If the eccentricity is less than 1, the orbit is closed. The object is bound to the sun. But if the eccentricity is greater than 1, the orbit does not close. It is an open curve. The object flies in, bends around the sun, and flies back out. It has too much speed for the sun's gravity to hold onto it. It was never captured. It was just passing through. This kind of path is called a hyperbolic orbit. 3I/Atlas has an eccentricity of 6.14. For comparison, a perfect circle is 0. Earth's orbit is 0.02. The most stretched comet might reach 0.99. 3I/Atlas is at 6.14. That is so far above 1 that there is absolutely no question. This object is not from our solar system. It never was. Now, you might wonder, if interstellar objects are real, why did we not find one sooner? Why did it take until 2017 to spot the first one? The answer is simple. We did not have the right eyes. For most of history, telescopes were pointed at specific targets. If something small and fast flew through, we would never have noticed. What changed was a new generation of automated sky surveys. Telescopes that do not wait for someone to point them. They scan the entire sky, night after night, automatically. The first system powerful enough to catch an interstellar intruder was Pan-STARRS on the summit of Haleakala in Hawaii. It had a camera with 1.4 billion pixels. And on October 19, 2017, that software flagged something strange. Robert Warwick at the University of Hawaii was going through the data when he noticed a faint moving dot. He ran the orbit calculations. The eccentricity came back as 1.2. It was the first interstellar object ever confirmed. They named it 1I/Oumuamua. And it was one of the strangest things anyone had ever seen. It had no coma, no tail. Based on its brightness, scientists calculated it was roughly 230 meters long, but only 35 meters wide. And then came the real mystery. Hubble found that it was accelerating, not by a lot, but just slightly. It was speeding up as it moved away from the sun. Gravity alone could not explain this. Some said maybe the gas was there, but invisible. Some said it might be an ultra-porous dust ball. Daryl Seligman proposed it could be a hydrogen iceberg made of frozen molecular hydrogen. And then Avi Loeb at Harvard proposed something far more controversial. He suggested Oumuamua might be an artificial light sail, possibly made by an alien civilization. But the truth is, we still do not know what Oumuamua was. By the time we realized what it was already heading away. We had only a few weeks to study it before it faded forever. Then, 2 years later, we got a second visitor, and this one was completely different. On August 30th, 2019, Gennady Borisov discovered a faint moving object using a telescope he built himself. Interstellar. They named it 2I/Borisov. ALMA in Chile detected carbon monoxide, and the levels were extraordinary, 9 to 26 times more than a typical solar system comet. It even broke apart. In March 2020, as it rounded the sun, the heat drove so much gas out that the nucleus cracked. Hubble photographed two separate pieces drifting apart. So, by 2020, we had seen two interstellar objects. One was dry and mysterious. The other was wet and chemically rich. They told us that the stuff between the stars is diverse. Then came the third one. On the morning of July 1st, 2025, the Atlas telescope in Rio Hurtado, Chile, flagged a faint moving object, 3I/Atlas, the most extreme visitor yet. Its orbit was almost perfectly retrograde. That means it was traveling in the opposite direction of all the planets, like a car driving the wrong way on a highway at double the speed limit. 3I/Atlas reached its closest point in late 2025, and this time we had months of warning. We had the most powerful telescopes in history already in orbit: Hubble, Webb, Swift, ALMA. And what they found was not what anyone expected. 3I/Atlas is a monster, roughly 2.6 kilometers across, the largest of the three interstellar objects by a wide margin. And it was active. Wildly active. Swift detected water nearly 3 units from the sun, where it should be too cold for water to boil off. It was releasing 40 kilograms per second. The water was coming from tiny ice-coated dust grains. Those small grains could absorb just enough sunlight to evaporate. The comet was spraying water where no one expected it. And then Webb looked inside. For the first time ever, they directly detected methane gas leaking out. Methane, locked deep inside the interior, only now being released. But the real shock came from ALMA. They were looking for something very specific: deuterated water, heavy water. The ratio of deuterium to hydrogen is like a cosmic thermometer. In 3I/Atlas, the ratio was more than 30 times higher than local comets. This implies the water formed in an environment colder than 30 Kelvin, colder than anywhere in our solar system's history. This comet was from a colder, older kind of star system. The chemistry locked inside this ice is telling us how the entire galaxy builds its worlds. A chunk of ice from another star flew into our solar system. We caught it early enough to point every major telescope on Earth and in space at it. Hubble photographed it. Swift detected water spraying off it from 3 times farther from the sun than Earth. Webb found methane leaking out of its interior for the first time ever. And ALMA discovered that the water inside it carries 30 times more heavy hydrogen than any comet born in our solar system. But what does all of that actually mean? What is this object trying to tell us? To answer that, you need to understand how scientists read the chemistry of a comet, because the atoms inside 3I/Atlas are not just atoms, they are clues, locked-in records of the place where this object was born, billions of years ago, around a star we have never seen. The key is something called isotopes, and isotopes are simpler than they sound. Think of it this way. Imagine a factory that makes chocolate chip cookies. Every cookie uses the same recipe, same dough, same shape. But some cookies come out of the oven with a few extra chocolate chips. They are a little heavier than the rest. They are still chocolate chip cookies. They taste the same, but if you weigh them, you can tell the difference. Atoms work the same way. Take hydrogen, the simplest element in the universe. A normal hydrogen atom has 1 proton. That is it. But there is a heavier version called deuterium. It has 1 proton and 1 neutron. Same element, same chemistry, but slightly heavier. Now, here is the important part. In extremely cold environments, chemical reactions naturally push more deuterium into water molecules. The colder the environment, the more heavy water you get. This happens because of a specific reaction in space. When a molecule called trihydrogen cation collides with deuterium hydride gas, the collision swaps a regular hydrogen for a deuterium. This reaction releases a small amount of energy, about 230 Kelvin worth. In a warm environment, the reaction can easily run in reverse, and the deuterium gets swapped back out. But in an environment colder than 30 Kelvin, there is not enough heat to run the reaction backward. The deuterium gets locked in permanently. So, when you measure the ratio of deuterium to hydrogen in a comet's water, you are reading a thermometer that has been frozen in place for billions of years. In Earth's oceans, the deuterium to hydrogen ratio is about 1.56 times 10 to the -4. In most comets from our solar system, it is roughly 1 to 3 times that value. In 3I/Atlas, the ALMA team led by Luis Salazar Manzano and Teresa Paneca Carreno at the University of Michigan measured a ratio more than 30 times higher than solar system comets. more than 40 times higher than Earth's oceans. They published this in Nature Astronomy in April 2026. A separate team led by Martin Cordner at NASA's Goddard Space Flight Center confirmed this using JWST, measuring a deuterium to hydrogen ratio of 0.95%, plus or minus 0.06. Both measurements point to the same conclusion. The water inside 3I/Atlas formed in an environment colder than 30 Kelvin. That is minus 406 degrees Fahrenheit, colder than anything in our solar system's history. But the thermometer was not the only clue. Cyrielle Opetom at the University of Edinburgh used the Very Large Telescope in Chile to measure two more isotopic ratios in the cyanide gas leaking from 3I/Atlas. The first was the nitrogen-14 to nitrogen-15 ratio. She measured it at 343. In solar system comets, this ratio is typically about 150. 3I/Atlas has more than double. Why does this matter? Because nitrogen isotopes are shaped by ultraviolet radiation. When a newborn star blasts its disk with UV light, it breaks apart nitrogen molecules. But here is the twist. The common version of nitrogen, nitrogen-14, is so abundant that it actually blocks its own UV wavelengths. It shields itself. The rarer version, nitrogen-15, is not abundant enough to do this. So it gets selectively destroyed, and its fragments get built into organic molecules like cyanide. This lowers the nitrogen-14 to nitrogen-15 ratio. A high ratio, like the 343 measured in 3I/Atlas, means very little of this UV destruction happened. The material was shielded from intense starlight. It formed either very far from its parent star or around a dim, low-energy star. The second ratio was carbon-12 to carbon-13. Opetom measured it at 147. The solar system average is about 89. Carbon isotopes tell a different story. Unlike hydrogen, which was made in the Big Bang, carbon is forged inside stars and scattered into space when those stars die. Over billions of years, the interstellar gas gets gradually enriched with the heavier version, carbon-13. So, a high carbon-12 to carbon-13 ratio means the material formed early in galactic history, when there had been fewer generations of stars to produce carbon-13. It is like a birth certificate, and 3I/Atlas's birth certificate says it is old. Very old. How old? A team at the University of Oxford, led by Matthew Hopkins and Chris Lintott, built a model to answer that question. They call it the Otaudahi-Oxford model. It works by taking the exact speed and direction of 3I/Atlas, tracing its path backward through the galaxy for billions of years, and comparing it to the known populations of stars. Their conclusion was striking. 3I/Atlas most likely comes from the thick disk of the Milky Way. In plain English, the thick disk is an ancient layer of stars that orbits above and below the main thin disk where our sun lives. These stars are old, metal-poor, and formed when the galaxy was young. The model gives 3I/Atlas a 68% chance of being older than our entire solar system. The best estimate is about 7 billion years old. Some calculations push it as high as 11 or 12 billion years. Think about what that means. Our sun is 4.6 billion years old. Earth is 4.5 billion. 3I/Atlas had already been drifting through the cold emptiness between the stars for roughly 2.5 billion years before our sun even started to collapse. It is a ghost from a star system that may no longer exist, a frozen relic from what astronomers call cosmic noon, the period between 9 and 12 billion years ago when the Milky Way was forming stars at its fastest rate. Hopkins said it plainly: all non-interstellar comets, such as Halley's Comet, formed at the same time as our solar system, so they are up to 4.5 billion years old. But interstellar visitors have the potential to be far older, and 3I/Atlas is very likely to be the oldest comet we have ever seen. Now let me put the full chemical picture together. The deuterium ratio says it formed somewhere colder than 30 Kelvin. The carbon dioxide to water ratio, measured by JWST at 7.6, is 4.5 standard deviations above the solar system average of 0.12. That means it formed far from its star, beyond the carbon dioxide snowline. The methane detection confirms this. Methane only freezes below about 20 to 30 Kelvin, so it had to form in the coldest outer reaches of its disk. The nitrogen ratio says it was shielded from UV radiation. The carbon ratio says it formed around an old, metal-poor star early in galactic history, and the kinematic model says it came from the thick disk and is about 7 billion years old. This is the first time scientists have ever been able to reconstruct the birth conditions of a planetesimal from another star system. Not a guess, not a model, actual measurements of actual material from an actual alien world. And it tells us that planet-forming disks existed around some of the galaxy's earliest stars in environments much colder and much less chemically enriched than our own. But here is the part that matters most. Despite all these differences, the basic ingredients are the same. Water is there, carbon dioxide is there, methane is there, cyanide is there, methanol is there. These are the same molecules that make up our comets. The same molecules that, according to many scientists, were delivered to the young Earth by comets and helped create the conditions for life. Teresa Paneque Carreño put it beautifully. She said, "Each interstellar comet brings a little bit of its history, its fossils, from elsewhere. We do not know exactly where, but with instruments like ALMA, we can begin to understand the conditions of that place and compare them to our own." Dennis Bodowitz at Auburn University said, "When we detect water, or even its faint ultraviolet echo, OH, from an interstellar comet, we are reading a note from another planetary system. It tells us that the ingredients for life's chemistry are not unique to our own." And that brings us to the biggest question of all. If comets like 3I/Atlas carry water and organic molecules between star systems, what does that mean for life? Scientists estimate that a typical star system ejects between 10 trillion and 100 trillion comets into interstellar space during its formation. Amaya Morrow-Martin at the Space Telescope Science Institute calculated this number by modeling how growing giant planets scatter leftover icy bodies. Between 90 and 99% of all planetesimals formed in the outer disk get flung into the void. Only 1 to 10% survive in structures like the Oort cloud. Scale that up across the entire galaxy, and the numbers are staggering. Astronomers estimate there are between 10 to the power of 25 and 10 to the power of 26 interstellar objects currently drifting through the Milky Way. That is more free-floating comets and asteroids between the stars than there are planets orbiting them. And their interiors are surprisingly well protected. Cosmic rays, the high-energy particles that fill interstellar space, can only penetrate the outer 2 to 5 meters of a comet's surface. For a nucleus the size of 3I/Atlas, roughly 1.3 kilometers in radius, more than 99.9% of the interior is completely shielded. Organic molecules, water ice, and prebiotic chemistry can survive intact for billions of years. Morrow-Martin found that when stars are young and still clustered together, up to 12 out of every 10,000 ejected planetesimals could be captured by a neighboring star system, but multiply it by trillions across billions of years, and the total exchange of material becomes enormous. This does not mean life itself travels between stars. That is the strong version of panspermia, and it remains highly speculative. But the softer version, sometimes called prebiotic seeding, is now supported by direct evidence. Interstellar comets deliver water and organic building blocks, the raw starter kit for chemistry that could, under the right conditions, lead to life. 3I/Atlas is the proof that this delivery system works. It carried water and organics across the galaxy for 7 billion years and dropped them into our solar system. If it had hit a young, rocky planet, instead of sailing past one, it would have delivered those ingredients directly to the surface. So, what happens next? We are building the machines to catch the next one. The European Space Agency is developing a mission called Comet Interceptor. It was approved in June 2022. The principal investigator is Geraint Jones at University College London. It will launch in late 2028 or early 2029 on an Ariane 62 rocket, riding alongside ESA's Aerial Exoplanet Telescope. After launch, it will park at the Sun-Earth Lagrange point L2, 1.5 million kilometers behind Earth, and then it will wait. For up to 3 years, it will sit there, doing nothing, until ground-based surveys spot an incoming long-period comet or a new interstellar object on a reachable trajectory. Then it will fire its engines and go. The spacecraft has 3 modules. The main spacecraft, built by OHB Italia, will fly about 1,000 kilometers from the target, acting as the communications hub. A European probe will fly closer, at about 850 kilometers, and a Japanese probe built by JAXA will fly closest of all, at about 400 kilometers from the nucleus. Together, the 3 modules will create a 3-dimensional profile of the comet's dust, gas, plasma, and magnetic environment. Could it have caught 3I/Atlas? No, the math does not work. 3I/Atlas was moving at 58 kilometers per second. Even if Comet Interceptor had been waiting at L2 when 3I/Atlas was discovered, matching that speed with chemical rockets would have been impossible. But that is exactly why the mission exists. It does not need to catch every interstellar object. It needs to catch one that comes in slower, or one that is discovered earlier. And with the Vera C. Rubin Observatory now online in Chile, carrying the largest digital camera ever built at 3.2 billion pixels, scanning the entire visible sky every 3 nights, we expect to find between 5 and 50 new interstellar objects over the next decade. Not one every few years, several per year. We are entering a new era. For the first time in history, we are not just looking at other star systems from a distance. We are touching pieces of them, actual physical pieces, chunks of ice and rock that were born around other stars, ejected into the darkness, and delivered to our doorstep by nothing more than gravity and time. Chris Lintott at Oxford said, "This is an object from a part of the galaxy we have never seen up close before. We think there is a 2/3 chance this comet is older than the solar system, and that it has been drifting through interstellar space ever since." Before 2017, we had 0 confirmed interstellar objects. Now we have 3. There is a parallel here that is worth thinking about. In 1794, a German physicist named Ernst Chladni published a book arguing that meteorites were actual rocks falling from outer space. The scientific community laughed at him. Within a decade, they realized he was right. Meteorites became our first physical samples of the solar system's formation. They changed everything we knew about how planets are built. Interstellar comets are the meteorites of the 21st century, except they are from everywhere. From stars that are still burning and stars that burned out long ago. From the deep, ancient history of the Milky Way itself. And the water inside 3I/Atlas. Water that is 30 times heavier than ours. Water that froze in the dark 7 billion years ago around a star we will never see. That water is telling us something simple and extraordinary. The ingredients for worlds like ours are everywhere. They have been everywhere for a very long time, and the universe has been delivering them between stars for longer than Earth has existed. If you want to understand the other great mystery-shaking cosmology right now, the force that makes up 68% of the universe and appears to be getting weaker, we made an entire video about it. It is right here. I will see you there.